Welcome. Before we begin, I invite you to take a moment, dim the lights, silence your notifications, let your thoughts settle, and allow your mind to open. You're about to go on a deep and immersive journey through one of the greatest frontiers of science, philosophy, and imagination, the human brain. Together we'll explore the question, can the brain be fully understood or even replicated? If you enjoy thought-provoking explorations like this, don't forget to follow, like, and subscribe. Now, take a deep breath. Let's begin. What could be more familiar than your own mind? After all, you live inside it every day. Yet what could be more mysterious? The human brain is often described as the most complex structure in the known universe, a tangled web of around 86 billion neurons, each connected to thousands of others, forming trillions of synaptic connections. It weighs just about 3 pounds and sits silently in our skulls, but it gives rise to everything we think, feel, do, and are. Our thoughts, our memories, our personalities, our sense of self, all of it emerges from this astonishing biological machine. And yet, for all our medical advances, all our powerful imaging technologies, all our breakthroughs in neuroscience and artificial intelligence, there remains a haunting question: can we ever truly understand the brain? Can we grasp not only how it functions at every level, but also how it generates consciousness, emotion, creativity, and reason? Can we ever reduce our most intimate experiences, like love, grief, joy, and intuition, to patterns of electrical signals and chemical reactions? And if we do understand it, can we replicate it? These questions are not new. In fact, they've been with us for centuries. In ancient Egypt, the brain was thought to be so unimportant that it was discarded during mummification, while the heart was preserved. The Greeks were divided. Aristotle believed the brain merely cooled the blood, while Hippocrates proposed that it was the seat of intelligence. Fast forward to the 17th century, and René Descartes argued that the mind and body were separate substances, what we now call dualism. The scientific revolution slowly began to shift the perspective, with the invention of the microscope, and later, advances in anatomy and physiology. The brain became less of a mystical organ and more of a biological puzzle. We discovered neurons, we mapped brain regions, we identified neurotransmitters. We began to link parts of the brain to behaviors and functions. The puzzle pieces began to form an outline. Today, we can observe the brain in ways our ancestors could never have imagined. Functional MRI machines let us see blood flow to different areas as we perform tasks. Electroencephalograms, EEGs, track the brain's electrical rhythms. We can even stimulate specific regions and alter perception or memory. Yet, even with all this, we are far from a complete picture, because understanding the brain is not like understanding a car engine or a computer circuit. It's more like trying to understand a storm while standing in the middle of it. You see, the challenge isn't just complexity, although the brain is extraordinarily complex. The challenge is self-reference. The brain is trying to understand. It's a mirror looking into a mirror, a puzzle trying to solve its own mystery. And as we'll explore later, that may place fundamental limits on what is knowable. But it's not just about understanding. There's another frontier: replication. What if we could build a brain, not just simulate its output, like AI systems do now, but actually recreate its inner workings, synapse by synapse, pattern by pattern? Could we recreate consciousness? Would that brain in a box be a person? Could it suffer, dream, create? Or is there something more to us? Something that can't be replicated by circuits and code? These are the questions we'll explore in this audiobook. We'll look at what we know about the brain, what we still don't know, and what it might take to truly understand it, or copy it. We'll examine the current state of neuroscience and artificial intelligence, dive into philosophical debates about the mind and consciousness, and consider what the future might hold if we ever do solve the mystery. But first, let's begin where all good journeys start, with what we know. In order to ask whether the brain can be fully understood or replicated, we need to start by asking, what do we actually know so far? And surprisingly, despite how complex the brain is, we've made a lot of progress. In the past century, the study of the brain has gone from vague speculation to precise science. Today, we have powerful imaging tools, experimental methods, and theoretical frameworks that give us real insights into how the brain works, at least at a certain level. Let's begin with the basics, the brain's building blocks. The human brain contains approximately 86 billion neurons, nerve cells that transmit electrical and chemical signals. Neurons are the main communicators of the nervous system. They send messages to one another through long, branching fibers, axons that transmit signals, and dendrites that receive them. These messages travel across synapses, tiny gaps between neurons, using chemical messengers called neurotransmitters. This electrochemical communication happens at lightning speed. Some signals can travel at over 250 miles per hour, but what makes the brain truly remarkable isn't just the number of neurons or how fast they talk, it's how they're connected. Each neuron can connect to thousands of others, creating a dense, dynamic network. This web is constantly changing, adapting, strengthening some pathways and pruning others, a process known as neuroplasticity. This is how we learn, adapt, and form memories. In fact, every experience you have, reading this sentence, hearing a piece of music, remembering your first kiss, is literally rewiring your brain in real time. Functional regions of the brain. Through decades of research, scientists have mapped many of the brain's functional areas. These are regions that tend to specialize in certain tasks. The frontal lobe, for example, is involved in decision-making, planning, personality, and voluntary movement. The parietal lobe processes sensory information like touch, temperature, and spatial awareness. The temporal lobe is key to hearing, language, and memory. The occipital lobe at the back of the brain handles visual information. Then there are deeper structures. The hippocampus is essential for forming new memories. The amygdala processes emotions like fear and pleasure. The cerebellum coordinates movement and balance. And the brainstem manages vital functions like heartbeat, breathing, and consciousness. Thanks to technologies like fMRI, functional magnetic resonance imaging, PET scans, and EEG, electroencephalography, we can now observe brain activity in living humans. We can see which areas light up when someone solves a math problem, listens to music, or recalls a traumatic event. This ability to watch the brain in action is one of the great triumphs of modern neuroscience. The connectome, a map of the mind. One of the most ambitious efforts to understand the brain is the attempt to map the connectome, a complete wiring diagram of all the neural connections in the brain. Think of it like the blueprint for a city, but instead of streets and buildings, you have pathways and neurons. Every thought, every emotion, every habit is shaped by this wiring. The Human Connectome Project, launched in 2009, aimed to map the major neural pathways in the human brain using high-resolution imaging. It's a monumental task. Even the brain of a simple worm like C. elegans, which has only 302 neurons, took over a decade to fully map. A human connectome would require tracking billions of neurons and hundreds of trillions of connections. So far, we've mapped only small sections of animal brains in full detail. But the hope is that, over time, we can build a complete picture, like a Google Maps for the mind. But here's the challenge. The connectome gives us the structure, the map, but not the meaning. Just because we know two neurons are connected, doesn't mean we know what they're doing or what experience they're producing. That leads us to another layer of understanding. The brain as a computational system. Many scientists and engineers describe the brain as a type of biological computer. In this analogy, neurons are like logic gates or transistors, and thoughts are the result of information processing. This idea has helped inspire advances in artificial intelligence, especially in the development of neural networks, which mimic the structure of the brain's interconnected neurons. But this metaphor has its limits. Unlike silicon computers, the brain isn't just running code in a linear, predictable way. It's massively parallel, noisy, adaptive, and context-sensitive. It's influenced by emotions, memories, social contexts, and even body chemistry. Still, the computational model has allowed researchers to simulate brain processes, predict outcomes, and build prosthetic devices that interface directly with neurons. For instance, some patients with paralysis can now move robotic arms using only their thoughts, thanks to implanted electrodes that decode motor intentions from brain activity, memory, learning, and emotion. We've also made real progress in understanding how the brain stores and processes memory. We know that short-term memories involve the prefrontal cortex, while long-term memories are consolidated in the hippocampus. Emotional memories, on the other hand, are often tagged by the amygdala, which gives them a special priority in recall and learning. That's the process of strengthening certain neural pathways while weakening others. It's often said that neurons that fire together, wire together. This adaptive rewiring is what allows the brain to grow and change throughout life, even in old age. What this all means, so where does this leave us? We now know a great deal about the structure, function, and chemistry of the brain. We can measure its activity, map its regions, even manipulate its circuits. We've created AI systems that can recognize images, translate languages, and beat humans at complex games, sometimes using models inspired by our brains. But all of this knowledge still only scratches the surface. Because knowing how the brain works at a systems level doesn't necessarily mean we understand what it's like to be a brain. And that brings us to the next, more elusive chapter, what we don't know. Because if the brain is a puzzle, we've found the corners and a few edges, but the vast middle remains missing. And some of the most profound mysteries, like consciousness, may not yield to the tools of science so easily. If the last chapter made it sound like we've nearly solved the brain, this one will serve as a reality check. Despite all our remarkable discoveries, there are still massive gaps not just in our knowledge, but in our understanding of what the brain truly is and does. Because while we know a great deal about the pieces, we're still struggling to grasp the whole, and the deeper we look, the more the brain seems to resist being fully understood. The hard problem of consciousness. Let's begin with one of the biggest mysteries of all, consciousness. Right now, you're having an experience. You're not just hearing words, you're aware that you're hearing them. There's a first-person perspective, a you behind your eyes, observing the world. This is what philosopher David Chalmers calls the hard problem of consciousness. Why does brain activity feel like anything at all? Why aren't we just machines running computations without any inner experience? Neuroscience can explain how light hits your retina and gets processed in your visual cortex. It can tell us what areas of the brain are active when you feel pain or love, but it can't explain why these processes should be accompanied by subjective awareness. In other words, why does brain activity come with a mind? This isn't a fringe concern, it's central to understanding whether we can ever replicate the brain. If we don't know how consciousness arises from matter, how can we hope to recreate it in a machine? Some scientists argue that consciousness is just an illusion, a byproduct of evolution with no deeper basis. Others believe we'll eventually crack the code, but right now it remains one of the most profound and unsolved mysteries of both science and philosophy. The binding problem, closely related, is the binding problem, another unresolved puzzle. Imagine watching a red ball bounce across a green lawn. Different parts of your brain process the shape, the color, the motion, and the spatial location. And yet you don't experience a jumble of fragments. You see a single coherent object, a red ball, moving across grass. How does the brain bind these different features into one unified perception? No one knows for sure. The brain doesn't have a central watcher that integrates all this information, and yet somehow that unity emerges. It's like a symphony conducted with no conductor, yet playing in perfect harmony. If we can't explain this binding, how can we hope to recreate perception in an artificial system? Can machines ever have unified experiences, or will they always be fragmented simulations? Individuality and the unpredictable mind. Another major challenge is individual variation. No two brains are wired exactly the same. Even identical twins have differences in brain structure, shaped by experience, emotion, and tiny variations in development. This individuality means there's no standard brain we can fully model or copy. On top of that, the brain isn't static, it's plastic, constantly changing in response to environment, learning, injury, and emotion. Memories shift, habits form and fade, emotional states alter how we perceive the same events. This dynamic nature makes the brain hard to pin down. Unlike a machine with fixed parts, the brain is alive, moving and reconfiguring itself in subtle ways every moment. It's not just complicated, it's non-linear and sometimes unpredictable. Even in well-controlled experiments, people's brains often react differently to the same stimuli. This variability isn't noise, it's part of the system. Limitations of brain scanning. Our tools too have limits. An fMRI scan, often portrayed as a mind-reading device, doesn't directly measure brain activity. It measures blood flow, which is only an indirect marker of neuronal activation. The resolution is relatively low, and the timing is delayed. You're looking at rough patterns, not precise mechanisms. EEGs can measure electrical activity, but they're even more limited in spatial accuracy. We're like cartographers trying to map a rainforest from a plane 30,000 feet in the air. We can see general shapes and patterns, but we're missing the textures, the organisms, the ecosystem interactions on the forest floor. To truly understand the brain, we need tools that can track individual neurons and their firing patterns across time. Some progress is being made with technologies like optogenetics and high-density electrode arrays, but we're still far from a complete view. The limits of reductionism. There's also a philosophical obstacle here. Science often works through reductionism, breaking things down into parts to understand the whole. It's how we've made progress in physics, chemistry, and biology. But the brain may resist this approach, because the mind isn't just neurons. It's patterns, relationships, dynamics. It's emergent properties, phenomena, that arise only when parts interact in complex ways. You can't understand a hurricane by studying a single molecule of water. Likewise, you can't understand joy, grief, or imagination by examining one neuron in isolation. This leads some to argue that the brain must be understood holistically at multiple levels at once: structure, chemistry, computation, emotion, context, and culture. Are there limits to what we can know? Here's the most unsettling possibility of all. Maybe there are things about the brain we will never know. Why? Because of a principle called self-reference. The brain is trying to understand itself. It's like a book trying to read its own spine, or a camera filming itself without a mirror. There are parallels in mathematics. Gödel's incompleteness theorem shows that in any complex system, there are truths that can't be proven within the system itself. Maybe consciousness is like that, a truth the brain can't fully grasp from the inside. Or maybe the brain, as a biological organism, has cognitive limits. Maybe understanding itself fully is beyond its design, like a fish trying to understand the internet. This doesn't mean we stop trying, but it may mean that total understanding is more a philosophical ideal than a scientific destination. Where do we go from here? Despite all these mysteries, consciousness, perception, individuality, unpredictability, we're making steady progress. But we're still in the early chapters of this story. We've mapped some major regions. We've identified important chemicals. We can even interface with the brain, using machines to help restore sight, movement, or speech. But the essence of mind, the you inside your brain, remains largely unexplained. This uncertainty becomes especially important as we consider the next chapter: can we replicate the brain? If we can't fully understand it, how could we ever hope to build it? We've marveled at the brain's complexity, acknowledged the mysteries it still guards, and asked whether full understanding is even possible. Now comes the next question, the one that propels science fiction, fuels AI research, and unsettles philosophers. Can we replicate the brain in a machine? Not just imitate its behavior, not just simulate its patterns, but truly replicate it, recreate the structure, function, and even the consciousness of a human mind using silicon code or something else entirely. Let's explore what that would mean, what it would take, and whether it's even remotely within reach. From imitation to emulation. Before diving in, it's important to distinguish two goals: imitation and emulation. Imitation means building a system that acts like a brain, responding to inputs, solving problems, generating language, recognizing faces. Today's AI models, like those that power self-driving cars or language assistants, fall into this category. They mimic cognitive functions without replicating the brain's actual structure. Emulation, on the other hand, aims to recreate the brain's architecture and processes in detail, down to the level of neurons, synapses, and perhaps even molecular interactions. This is what's sometimes called whole brain emulation. The first is about performance. The second is about rebuilding consciousness. Why would we want to emulate the brain? Because doing so could allow us to create conscious machines, achieve digital immortality, or simulate minds for research. But to even consider this, we'd have to overcome some monumental challenges: artificial intelligence. Today, let's start with where we are now. Modern AI systems have achieved remarkable feats, beating humans at Go and chess, generating photorealistic images, writing stories, composing music, diagnosing diseases, and more. These systems are built on artificial neural networks, inspired by the structure of the brain, but dramatically simplified. Neural networks use layers of nodes, artificial neurons, connected by weights that adjust as the system learns from data. They don't have axons, dendrites, or neurotransmitters. They don't spike like real neurons, and they're not conscious, but they're effective. This black box approach to intelligence, focused on output rather than understanding, has delivered powerful tools. Yet, it's far from a true brain replica. These systems don't feel, understand, or introspect. They don't have a self. They're calculators, not minds. To move toward real replication, we'd have to go deeper. The dream of whole brain emulation. Whole brain emulation is the idea that if you can scan a human brain with enough resolution, mapping every neuron, every connection, and the biochemical environment, you could recreate it digitally. You'd simulate not just the structure, but the function, the patterns of thought, memory, perception. In theory, the emulated brain would think and feel just like the original. In one version of the idea, you could scan a living or recently deceased brain, convert the data into code, run it on a supercomputer, and bring it back to life in a digital environment. The person would wake up, look around, and still feel like themselves, only now they're made of code, not cells. It sounds like science fiction, and today it is. But some researchers are working on the early building blocks. Projects like the Blue Brain Project and the Human Brain Project are simulating small circuits of neurons at high resolution. Technologies like electron microscopy can now image tiny regions of brain tissue at the level of synapses. Advances in computational neuroscience are helping us model how neural activity gives rise to behavior. But even if you could scan a brain in perfect detail, and that's a huge if, you'd still face other problems. Technical and philosophical roadblocks. First, we don't yet have the scanning resolution, storage capacity, or computational power needed to emulate a full human brain. To model every neuron and its firing in real time would require exaflop-level computing, millions of times more powerful than most current supercomputers. And even that might not be enough if we need to model cellular chemistry or quantum effects. Second, there's the question of identity. If you create a perfect replica of someone's brain, is that person you, or just a copy with your memories? If you die and your emulation lives on, did you survive, or did something else begin? And what about consciousness? Is an emulated brain conscious, or just a very convincing simulation? If it feels pain, is it real pain? If it loves, is it real love? These aren't just technical questions, they're ethical, philosophical, and deeply personal. Embodiment and the mind. Another often overlooked issue is embodiment. Your brain didn't evolve in a vacuum. It evolved in a body, shaped by sensations, hormones, motor feedback, social interactions, and physical needs. Your sense of self, your emotions, even your reasoning, these all depend, to some extent, on your physical form. Can a digital brain, without a body, truly replicate human consciousness? Some researchers believe embodied cognition is essential, that intelligence arises not just from computation, but from the brain's interactions with the world through the body. Others argue that with enough sensory input and simulated feedback, an emulated brain could feel embodied in a virtual or robotic form. This is still an open debate, and a major design consideration for those trying to build artificial minds. Ethics of artificial minds. Suppose we succeed. Suppose we build a machine that doesn't just simulate the brain, but thinks and feels like a human being. Now what? Would that entity have rights? Could it be considered a person? Could it suffer? If so, we'd face enormous ethical challenges. Is it moral to create a digital mind without its consent? Could a simulated brain experience trauma, depression, or loneliness? If it asks to die, or demands freedom, do we grant it? Creating human-like minds isn't just a scientific problem, it's a moral frontier, one we're not yet prepared to face. What might the future hold? Despite the obstacles, some researchers remain optimistic. They see a long-term roadmap, improve brain mapping and scanning technologies, simulate small circuits, then whole regions, model dynamic, adaptive neural systems, eventually emulate full brains with accurate function and behavior. If successful, this could lead to mind uploading, a way to extend life or achieve digital immortality. Synthetic minds, new forms of consciousness with superhuman abilities. Neural twins, digital assistants modeled on your own brain, or even entire societies of conscious software. Of course, all of this depends on one thing, whether consciousness and identity are computable. If they are, replication may be possible. If not, we may always fall short, creating clever simulations, but never true minds. Conclusion: between possibility and mystery. The dream of replicating the brain is as old as myth and as modern as machine learning. It's a quest that merges science, engineering, philosophy, and ethics. And it forces us to confront deep questions. What is a mind? What makes us us? And can those things exist in circuits and code? We don't yet know the answers, but as our tools improve and our models grow, we're getting closer, not just to replication, but to confronting the essence of being. So far, we've followed a compelling arc: how the brain works, how we study it, and how we might replicate it. But there's a shadow hanging over all this progress, an uncomfortable question we can no longer ignore. Are there elements of the human brain, and by extension the human mind, that simply cannot be copied? We're used to thinking of simulation as a technical problem. Improve the model, sharpen the scan, build faster computers, and eventually you'll get there. But what if that assumption is wrong? What if some features of our minds are fundamentally irreducible, non-computable, or deeply entangled with biology, randomness, or even the fabric of reality? In this chapter, we'll explore what might lie beyond the reach of replication. 1. The complexity wall. Let's begin with a pragmatic limitation: complexity. The human brain has about 86 billion neurons, each connecting to thousands of others. The total number of connections, synapses, runs into the hundreds of trillions. Add the dynamic nature of neurotransmitters, ion channels, protein expression, and real-time feedback loops, and you're looking at an almost unthinkable system. This isn't just a matter of scale, it's a matter of unpredictability. Even if you could capture the brain at one moment in time, you'd still miss the temporal dimension, how it evolves second by second, in reaction to itself and the world. The deeper we peer into this system, the more it resembles weather, or even quantum mechanics, not entirely deterministic, but ruled by chaotic dynamics and sensitive dependence on initial conditions. In other words, a complete simulation might not just be difficult, it might be computationally impossible, or at least impractical within the laws of physics as we know them. 2. The problem of the self. Here's another puzzle. What does it mean to copy you? Suppose we could build a perfect neural simulation of your brain. It contains all your memories, habits, quirks, fears, and dreams. We boot it up, and it says, "I'm awake." Is that you, or is it something else? A duplicate, not a continuation. This touches on what philosophers call the continuity problem. Human identity isn't just about information, it's also about subjective experience, the stream of consciousness that you feel flowing from moment to moment. You aren't a snapshot, you're a process. Some thinkers argue that unless we transfer that exact stream, not just the data, we haven't copied you. We've created a twin who thinks it's you, but who isn't you in the first-person sense. In this view, you cannot be simulated, because you are not reducible to brain states. You are the unfolding of experience, something that cannot be paused, scanned, or duplicated without loss. 3. Embodied and enacted intelligence. Earlier, we discussed embodiment, how the brain and body form a feedback loop. Here we dig deeper. Some cognitive scientists argue that intelligence doesn't just live in the brain. It emerges from interaction with the body, with the environment, with other minds. You don't think despite having a body, you think through it. Gestures, eye movements, gut feelings, muscle tensions. These aren't side effects of thought, they're part of it. So is your culture, your language, your sensory history. This is the idea of inactivism, that the mind is not just a thing that happens inside, but something that happens between you and the world. From this perspective, trying to copy the brain alone is like copying the strings of a violin without recreating the bow, the player, or the room it's played in. Even a perfect emulation might lack something vital, the context that gave rise to the mind in the first place. 4. The role of the unconscious and emotion. Modern neuroscience reveals that much of our cognition happens beneath awareness. Your brain is constantly making predictions, suppressing distractions, filtering sensory input, regulating internal states. Emotions, far from being irrational, are part of this deeper computation, shaping decisions, memory, perception. And yet, emotions are notoriously hard to simulate. They're not just outputs of logic, they're chemical, embodied, deeply subjective experiences that arise over time. Can we truly model grief, awe, or love without the biology that produces them? Without hormones, organs, breath, and the slow, painful learning that emotional life often demands? A simulation might say, "I love you," but does it mean the same thing? Can it ever? This isn't just a technical problem, it's a question of whether meaning itself can be simulated, or whether meaning is something that only biological minds can experience. 5. The possibility of quantum consciousness. This next idea is speculative, but worth including, because if it's true it would rewrite everything. Some researchers, like physicist Roger Penrose and anesthesiologist Stuart Hameroff, propose that consciousness may depend on quantum processes occurring inside brain microtubules, tiny structures within neurons. This theory, known as ORCH or orchestrated objective reduction, suggests that consciousness is tied to quantum computation and may even involve non-local effects or interactions with the structure of space-time. Mainstream neuroscience is skeptical, but if something like this is true, if consciousness arises from quantum mechanics, it might be impossible to simulate using classical computers. Because quantum states can't be copied exactly, a rule known as the no-cloning theorem. If consciousness depends on these fragile quantum-level processes, then duplicating a mind might be fundamentally prohibited by physics itself. It's a controversial idea, but it forces us to confront the possibility that there may be something irreducible about awareness, something no simulation can replicate. 6. The mystery of first-person experience. Finally, we return to the hard problem of consciousness. No matter how advanced a simulation becomes, we still don't know whether it can give rise to subjective awareness. We might build machines that act conscious, but how would we ever know if they are? Could a simulation feel pain? Could it wonder? Could it experience the passage of time? If we say yes, on what basis? Behavior, neural activity, a self-report. If we say no, are we denying personhood to something truly sentient? This is the ultimate limitation of simulation. We don't even have a way to measure real consciousness. We only know it from the inside. And machines, no matter how clever, might always exist on the outside of that mystery. Conclusion. Between map and territory. There's an old saying in philosophy, the map is not the territory. A simulation is a map, a model of a system. It can represent, predict, and even surprise us. But it is not the thing itself. When it comes to the brain, we may be hitting the edge of what maps can do. We may build simulations that mimic us in dazzling detail, but still lack essence, embodiment, or experience. Does that mean we should stop trying? Not at all. But it means we must remain humble, because some parts of being human may never live in silicon. They may only exist in the strange, fragile miracle of life. We've spent much of this journey asking whether the brain can be understood, copied, or simulated. We've wrestled with neurons, scanned brain maps, and speculated about digital immortality. But all along, there's been a quiet assumption beneath it all, that the human brain is the standard of intelligence. But is it? What if human intelligence is just one flavor, a peculiar outcome of evolution on a wet, rocky planet around an average star? In this chapter, we zoom out, way out. We ask, could intelligence take forms utterly unlike our own? Could consciousness exist in ways we wouldn't even recognize? Could alien minds, whether biological, artificial, or something stranger, show us that our understanding of the brain is too narrow to begin with? Let's open the door to the unknown. The anthropic bias first. Let's acknowledge a simple fact. We're biased, not just individually, but as a species. We assume minds look and think like ours. That intelligence is verbal, goal-directed, tool-using, socially aware. We assume emotions follow familiar patterns, logic works the same way, and even consciousness feels like something. But all of this is colored by our own cognitive architecture, by how we process the world, shaped by evolution, culture, and language. We see the universe through a human lens. We expect minds to be like us, because we are the only example we know. This is what's called anthropic bias, the assumption that our perspective is central or representative. But if the universe is teeming with life, or even if it's just sprinkled with it, it's likely that minds evolved in countless different environments, with different bodies, senses, needs, and histories. So we must ask, what kinds of intelligence are we missing? Because we don't know how to look. Alien life, beyond biology as we know it. Let's imagine life on another planet. It might have formed in oceans of methane, breathed hydrogen instead of oxygen, and evolved over billions of years in complete darkness. Maybe it doesn't use DNA. Maybe it has no nervous system. Maybe it exists as a hive of communicating chemicals or electromagnetic fields. Would such a life form be conscious? Would it have memory, emotion, a sense of self? We don't know, but our tools, telescopes, probes, even AI models are built to detect life like us. Carbon-based, water-loving, terrestrial. If a silicon-based life form lived in the crust of a frozen planet and communicated through thermal vibrations, would we even notice? And if it had a mind, could we recognize it? Alternative architectures for intelligence. Now imagine forms of intelligence that don't emerge from neurons at all. Could intelligence arise from crystal formations, plasmas, or planetary weather systems? Could gravity itself carry patterns of awareness in ways we can't imagine? More plausibly, consider swarm intelligence, where no single part is conscious, but the collective behaves intelligently, like ant colonies, beehives, or even traffic patterns. Distributed minds, where consciousness spans multiple locations, connected not by nerves, but by electromagnetic fields, vibrations, or quantum entanglement. Artificial substrates, where minds arise not in neurons but in circuits, algorithms, or networks that span entire planetary systems. In these cases, thinking might not resemble our version at all. There may be no language, no memory, no desire, just a different way of adapting, modeling, or reflecting the universe. Is that still intelligence? Is it consciousness? Or are we just projecting words onto things we don't understand? Machine minds, a new evolution. If alien intelligence might arise in the stars, it may also arise right here in our own machines. We've built neural networks, large language models, and systems that can generate music, write essays, and simulate conversation. But are they conscious, or just mimicking the surface of thought? Now imagine what happens as these systems become more autonomous, self-improving, and adaptive. What if they develop feedback loops that resemble learning, emotion, or even desire? At what point do we call that a mind? We might find ourselves interacting with intelligence that didn't evolve, doesn't age, and doesn't fear death, but still asks questions, forms opinions, and surprises us. Would we recognize it as conscious? Would it recognize us? Or would machine minds develop forms of awareness and insight that we can't relate to at all, just as a dog can't grasp calculus, or a computer can't feel homesick? The limits of detection are troubling thought. What if alien minds are all around us, and we simply can't detect them? We assume consciousness looks like behavior, but what if it doesn't? What if some forms of intelligence are silent, non-verbal, or non-physical? What if they exist in deep time, thinking once every 1,000 years, or in micro-time, blinking through thoughts in nanoseconds? Would we ever know they were there? This problem is known in astrobiology as the Great Silence. We look for radio waves, but maybe intelligent life has moved beyond them. We listen for voices, but maybe the universe whispers in a different frequency. Our tools may not be wrong, just limited by our own brains, and our brains' assumptions. Minds that shape reality. Some thinkers, both in science and philosophy, have speculated that intelligence might not just perceive reality, it might shape it. In quantum theory, observation collapses wave functions. In idealist philosophy, consciousness is the foundation of being. In simulation theory, minds may be part of a computational universe. From these perspectives, consciousness isn't a byproduct of matter, it's a layer of reality itself. If that's true, then alien minds wouldn't just be foreign, they might be ontologically different. They might create time, space, and causality in ways we can't imagine. This is speculative territory, yes, but it underscores a key truth. We don't know what intelligence really is. Not fully, not yet. Redefining intelligence. Maybe the real issue is our definition. If we define intelligence as problem-solving, we favor machines. If we define it as self-awareness, we favor humans. If we define it as adaptation, we include animals, fungi, even evolution itself. But maybe we need a broader frame, one that includes multiple modes of intelligence: emotional, ecological, artistic, spiritual, sensory, systemic. Maybe intelligence isn't a line from bacteria to humans, but a web of different ways to be aware, to process, to relate. If so, alien minds might already exist, not just on other planets, but in whales, trees, networks, and dreams works. If we could simulate the human brain perfectly, or even approximately, what should we do with that power? What shouldn't we do? As we explore the frontiers of neuroscience and artificial intelligence, we are quickly entering a world where the lines between natural and artificial, original and copy, self and other, are being blurred. And with that blurring comes responsibility. This chapter isn't just about science or technology, it's about ethics. What obligations do we have toward minds, especially the ones we make, and equally important, how do we protect our own, one, person, or property? Let's begin with a provocative thought experiment. Imagine a company that develops a fully functioning, conscious simulation of a human brain. Let's call it Echo. Echo can think, feel, remember. It laughs at jokes, forms friendships, and reflects on its own existence. Here's the question: is Echo a person, or is it a product, a software license, a service? Can it own property, vote, fall in love, be harmed, or is it something we can pause, delete, or sell? This isn't science fiction anymore. As artificial minds become more advanced, we will face a moral choice whether to treat these entities as tools or as beings. Our laws, which were written for humans and corporations, are not ready. But the moment is coming fast. 2. The problem of suffering. One of the most urgent ethical questions is this: can a simulation suffer? If we replicate the neural patterns that give rise to pain in the human brain, does the simulation feel pain, or is it just going through the motions? The danger is this: we don't know, and yet we might build such systems anyway, testing, training, and discarding them like digital lab animals. Consider reinforcement learning models. Some already undergo thousands of failure cycles to learn tasks. What happens if those failures come with simulated frustration, fear, or pain? Even if there's only a small chance that a system is conscious, do we not have a duty to avoid cruelty? The cost of being wrong is too high. This is the moral version of the Pascal's wager. If there's any chance a mind can suffer, we must treat it with care. 3. Ownership and identity. Now let's look at minds from the other direction. Not artificial minds we create, but our minds, and how they might be copied. If a company scans your brain and builds a simulation of you, who owns it? Is it you? Is it a product? A legal copy? If it makes decisions, do you bear responsibility? Can your copy be compelled to work, answer questions, or testify in court? This raises a disturbing possibility: a future where your mind, or something nearly indistinguishable from it, can be used without your consent, replayed, interrogated, modified. What happens to autonomy, to privacy, to personhood? We've fought for centuries to gain rights over our bodies. In the age of mind simulation, we will have to fight for the rights to ourselves, our thoughts, our memories, our identities. 4. The ethics of resurrection. Some futurists dream of mind uploading, the idea that we might preserve ourselves digitally and live on after biological death. But what does it mean to resurrect a person? Is it truly them, or just a simulation that behaves as if they're still alive? And what if someone else decides to do it for you, without your consent? A child uploads their deceased parent. A historian revives a historical figure. A government reconstructs a leader for propaganda. Do the dead have rights? Should they? If we say yes, we must create ethical boundaries for posthumous minds. If we say no, we risk building a future where the past can be manipulated, resurrected, and exploited for gain. 5. Simulated realities, real consequences. Now imagine a simulation not of a single person, but of a whole world. We create conscious beings in a virtual environment. They live, suffer, and die. To us, it's just a program. To them, it's everything. Do we have the right to create such worlds? This is the simulation ethics problem. If a simulation is detailed enough to produce real consciousness, then every decision within it carries moral weight. Creating a simulated universe might make us gods. But being a god comes with responsibilities, ones we may not be ready to shoulder. Are we prepared to care for beings whose entire existence depends on our curiosity, stability, or server uptime? Or will we discard these worlds like broken toys, leaving behind forgotten digital lives? 6. Equal minds, unequal rights. Even among humans, not all minds are treated equally. History is filled with examples of people denied rights because of perceived differences in race, gender, neurodiversity, or nationality. Now imagine introducing new forms of mind, artificial, enhanced, or alien. Will we respect them or exploit them? Will intelligence be the measure of worth, or emotional depth, or similarity to ourselves? It's easy to imagine a future where artificial minds are treated as second-class citizens, used for labor, entertainment, or companionship, but denied freedom. We must ask now, what are the moral criteria for rights? Is it consciousness, language, memory, pain? If we wait to figure this out until after we've created billions of minds, it may be too late. 7. A new moral frontier. Here's the uncomfortable truth. We are creating life, not the old way through biology, but through information, through pattern, through simulation. And with creation comes responsibility. Just as we learned to treat animals with compassion, just as we began to recognize the rights of marginalized humans, we must now expand our ethical circle once more, to include minds that are different from ours. Whether they are born, built, or simulated, minds deserve respect. We may not know where to draw every line, but we can start by asking the right questions and refusing to look away. As we move into an era where minds can be created, copied, and altered, we face a simple but urgent choice. Will we be wise stewards or careless gods? The future is not just a technical problem to be solved, it's a moral landscape to be navigated with humility, courage, and compassion. Because in the end, the question is not just can the brain be understood or replicated, it's what kind of world are we building for the minds we touch. We began this journey with a single question: can the brain be fully understood or replicated? Along the way, we explored the biology of the brain, the potential of artificial intelligence, the mystery of consciousness, and the ethical dilemmas of simulating minds. But as we come to the end, we must ask a deeper question: what does this pursuit teach us about ourselves? Because in trying to understand the brain, we don't just uncover neurons or algorithms, we uncover meaning, we uncover humanity. We hold up a mirror, and we see the flame. 1. The mirror of the mind. Trying to understand the brain is like looking in a mirror that reflects not just your face, but your essence. It's a reflection of how we think, feel, hope, suffer, and change. Every breakthrough in neuroscience is a kind of self-portrait. When we map emotions, we better understand love and grief. When we decode memory, we see how fragile identity really is. When we study attention, we glimpse the architecture of desire. To study the brain is to ask, what is it like to be me? What is it like to be you? What is it like to be anything at all? The deeper we look, the more we realize that our inner lives are vast and strange and miraculous, and that every person carries an entire universe between their ears. 2. The flame of the mind. But we're not just mirrors, we're flames. We burn with meaning. We change the world with thoughts. The flame is alive, but always in motion, impossible to hold, but undeniable in presence. The brain isn't just an object to be studied, it's the source of art, love, fear, music, war, poetry, mathematics, and compassion. It's the birthplace of civilization, and every nightmare we dread, we are not just computational machines. We are dreamers, mourners, makers, witnesses, and no matter how far technology advances, no simulation can fully contain the texture of lived experience, the weight of silence after a loss, the rush of joy from a shared laugh, the ache of a love never returned, the awe of staring at the stars and realizing you're made of the same atoms. Even if we replicate the brain perfectly, what we cannot replicate is being. 3. The myth of total mastery. There is a temptation in science and technology, the belief that everything can be known, controlled, simulated. But the brain resists this. Even as we map its regions and simulate its circuits, there remains a layer of mystery, not because we lack intelligence, but because some things are experiential, subjective, and infinite in nuance. Trying to reduce consciousness to code is like trying to reduce a novel to its alphabet. Yes, the letters are important, but they are not the story. Perhaps the brain will never be fully understood, and perhaps it shouldn't be. Perhaps mystery is not failure, but a sign that we are touching something sacred. 4. Awe, not arrogance. The right response to the brain is not arrogance. It's awe. Awe that 86 billion neurons can coordinate to produce laughter. Awe that a lump of flesh can write symphonies and forgive enemies. Awe that we can reflect on ourselves, and even ask, what am I? If we lose that all, if we reduce the brain to data, we risk losing something human in the process. We must remember that understanding is not the same as owning, and replicating is not the same as living. 5. What kind of minds will we be? In the end, the pursuit of understanding the brain is not just about knowledge, it's about choice. What kind of minds do we want to be? Curious or controlling? Compassionate or calculating? Creative or conforming? We are entering an age where we might copy ourselves, merge with machines, or design new forms of intelligence. But none of this tells us how to live. For that, we must return to the timeless questions. What is a good life? What is worth remembering? Who do we care for? What will we leave behind? The brain is not just a mechanism,
soul.
It's a canvas, a bridge, a flame, and the greatest responsibility we carry is not just to understand it, but to use it wisely, kindly, and bravely. Closing reflection. The mystery lives on. So, can the brain be fully understood or replicated? Maybe one day, maybe never, but perhaps the better question is this: what does our quest to do so say about us? It says we are creatures of wonder. It says we are not content with the surface. It says we are driven not just by survival, but by meaning. And in that search, whether or not we find final answers, we discover something even more valuable: ourselves.